Now we could see this, right? N choose R, n factorial over n minus r factorial, and n minus r. This is n factorial over n minus r factorial, n minus r factorial. So they're the same, right? Because that's just r factorial. So these are equal. Okay. We have another identity here. So I have this identity. N choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r. This is very useful. And let's just check out and see that it works. So if I have 5, choose 3, say, we know that is 5 times 4 divided by 2, so that's 10, right? So this should be equal to, we're checking, this should be equal to 4, choose 2, plus 4, choose 3. 4, choose 3, the number of ways to pick 3 from 4 is the number of ways to exclude 1 from 4. So this is 4. And the number of ways to pick 2 from 4, well, that's 4 times 3, which is 12 divided by 2, so that's 6. So we see these are equal, so yes. Okay, not a proof, but certainly true. So for a proof, let's just give a little, what's called a little counting or probabilistic argument here in general. So this is a proof. So proof of the identity is that what I can do is isolate one of the R objects, any one, and call it Dave. You could call it anything you want. So then count number of combos of size R from N, including Dave, and also not including Dave. Okay, so if I include Dave in the count, then I've removed Dave, so including Dave. This is the same thing as removing Dave from the count of what's left, because I'm definitely going to include him, so there's n minus 1 left to pick from, and I only need r minus 1 ways to include Dave. Right, because I pick Dave, and then there's n minus 1 choose r minus 1 ways to pick the remaining. So then not including Dave, well, I'm not including Dave. So that means Dave's still not in the pool to pick from. So it's still n minus 1, but now I need all r, right? So that's ways without Dave. And I add them together. Okay, so that's my proof. All right, it's very useful identity. You can also prove this directly if you want by just using the formulas. It's not as interesting, I don't think. All right, we're getting there. We're going to just talk about the binomial theorem now and the multinomial theorem fairly quickly. We want to do the proof of it, and that's the main thing. So I think this is, at most, this will be this lecture and one more. So let's start with the binomial theorem. Okay, so theorem. If I have a binomial in algebra, x plus y to the nth power, then I can express it this way, as the sum k equals 0 to n, choose k, x to the k, I guess, y to the n minus k. It doesn't matter. You could do it either way. Okay. Now, maybe we should see this. So for example, let's say we have x plus y to the 4th power, something like this. Then this is equal to 4 choose 0. So I would have the y first, right? So I have 4 choose 0, that's 1. So I have y to the 4th plus 4 choose 1, that's 4. I have y cubed x plus 4 choose 2, that's 6. I have y squared x squared plus, now they go back the other way, 4 choose 3, that's 4. I have y x cubed, and finally 4 choose 4, and that's x to the 4th there. Okay, so this is a way to quickly write down to expand binomial terms. How to prove it? Let's do the proof. I'm a little worried we're going to get cut off in the middle. So well, I don't think we will. So let's try it. Actually, let's just stop the video and we'll do it in the next one. Okay, so we'll do the proof in the next one.